Right. Thanks everyone for coming to this talk. Today, Haripriya will be telling us about weighted multi-commodity flows over time. Haripriya, feel free to start whenever you're ready.
Okay. Thank you. So I'll be talking about weighted maximum multi-commodity flows over time. And this is the problem that I've been working on for the past couple months with Jochen and Madison. But before I get into what exactly is a flow over time, I think I'd like to first motivate why one should care about flows over time. So this is a pretty straightforward transportation problem. We have some warehouses, some destinations, and we want to ship product from the warehouses to the destinations. And as most of you know, we can represent this as a network. Perhaps it's not a fair assumption that all arcs have infinite capacity. So let's add some capacities on these arcs. And then sending product from one of these red sources to a white sink can be modeled as a flow in this network. But I claim that this doesn't really capture the whole picture, because in this network, a flow is instantaneous, travels instantaneously. While in our actual problem, as much as we'd like road travel to be instantaneous, the truth is it's not. That is, these arcs have some transit times associated with them. It takes a certain amount of time to go from point A to point B. So when I add these transit times to the edges in my network, now it represents the problem better. It's a better representation. But unfortunately, our traditional notion of static flows doesn't work very well in this network. The reason is that we need to worry about what time the flow arrives on an edge to ensure capacity constraints are respected. So we need a different notion, and that's where flows over time come in. Essentially, in a static flow, what we do is we define the amount of flow on an arc. In a flow over time, we're going to define the rate of flow entering arc E at time theta. So there's some things we need to keep in mind here. First of all, if we want to talk about the outflow rate, so the rate at which flow is leaving arc E, we need to rewind to the point in time when that flow first entered the arc. If tau E is the transit time for arc E, this is precisely time theta minus tau E is when the flow first entered the arc. So the outflow rate is equal to this quantity here. The other thing we need to be careful about is typically we talk about amounts when we're talking about flow conservation or for the objectives of certain problems, objective functions of certain problems. And so here we're talking about rate of flow. So it's not really the same thing. We need to integrate over the desired time window. So we define the excess at node B and time theta as follows. It's the total amount that has entered B by time theta minus the total amount that has left B by time theta. And then one last point, I suppose, is the time horizon capital T. This is essentially the hard deadline by which all flow must have reached its destination. So after this time T, there's no flow moving in the network. So it's true that we defined flow over time to be any Lebesgue integrable function, but for the purposes of this talk, we're only considering piecewise continuous functions. So it's sufficient to just define the flow at capital T points in time for any interval theta, theta plus 1, the flow will be constant in this interval. The rate of flow will be constant in this interval. So before I move on to the next slide, are there any questions about the definition of flows over time so far? Okay, I'll try and pause periodically, but please feel free to interject if you have questions. So we'll warm up, I suppose, with the maximum ST flow over time problem. So the max ST flow over time problem is we have capacities and transit times for every arc. Then we have a source node S and a sink node T, and of course the time horizon capital T. So our objective is we want to find a feasible ST flow over time which maximizes the value of F, which is the total amount of flow that reaches T. So it's the integral over the time interval 0 to T. And we say that a flow is feasible if it satisfies weak flow conservation constraints. So that means that we're allowed to store flow at intermediate nodes when theta is between 0 and T. But at time T, then we shouldn't be storing flow anymore. Like the flow should be completely gone by that point. The main thing is we're not allowed to send out more flow than we've received at any point in time. So the max ST flow over time problem can be solved in polynomial time. Ford and Fulkerson give an algorithm for doing so, and their algorithm uses the notion of temporally repeated flows. So essentially the idea of a temporally repeated flow is this. We take a static ST flow X, and we think of XP to be the rate of flow on the path P. And then what we'll do is we'll keep sending flow at this rate along P as long as there's enough time left for the flow to reach the destination by time capital T. So that's essentially what we're saying here. We're going to start sending flow, and as long as there was enough time for the flow to have reached B by time theta, and there is enough time left for the flow to go from V to T, we'll keep sending flow at time theta. And the rate will be XP. When this is no longer true, we stop sending flow, we turn off the faucet at that point. So this is best explained with a picture. So in this network, all arcs have capacity 2. The numbers on the arcs denote the transit times. And P1 is this top path, P2 is this bottom path. We're going to, by definition of temporally repeated flows, we're going to send flow along P1 at rate 1 and along P2 at rate 2. So at time 1, we're sending flow from S along both of these paths at their respective rates. And then when we get to time 2, we still continue pumping flow from S to T along the bottom path. But we turn off the faucet for this top path because the total transit time here is 4, the total transit time for the path, and the time horizon is 5. So the flow won't reach in time if we were to keep pumping flow. So we have to turn off the faucet at time 2. Then time 3, we still can send more flow along the bottom path and it will reach in time since the total transit time of this bottom path is 2. But then at time 4, we need to once again turn off the faucet and everything's reached its destination by the time horizon. So essentially the main idea is this: given a feasible static ST flow X, if we have the decomposition of X with respect to paths and cycles, then we can compute the corresponding temporally repeated flow F. Note that we're going to ignore flow in cycles. We only care about the flow sent along paths. And this satisfies strict flow conservation constraints. We never store the flow at any point, so the excess at any node at any given point in time, any intermediate node at any given point in time is 0. So what's the value of this temporally repeated flow F? The value is this quantity here. Essentially, it's the rate at which we're sending flow times the amount of time for which we're sending flow along that path. And we can rewrite this expression here as in this form. And that makes it easier for us to compute X that maximizes this quantity. So this essentially is what the Ford-Fulkerson algorithm for max ST flow over time does. We first compute a feasible static ST flow X, which maximizes this quantity. And then we compute a flow decomposition and output the corresponding temporally repeated flow. And note that the value of F is equal to this. So step 1 can be computed. This is more of an aside, but we can actually cast it as a min-cost circulation problem by adding an artificial arc TS with infinite capacity, and we'll set tau, tau of TS to be minus T. So now the costs in this min cost circulation problem are in fact the transit times. And so we get that maximizing this is equivalent to minimizing this quantity, which is precisely the cost of a circulation X in this modified network. But that's more of an aside. I'm not going to get into the details of how we prove this returns an optimal solution, but roughly what happens is we can define the notion of an ST cut over time to be, it's similar to the static counterpart, except that, so for every node, we define the time at which it crosses from the S side of the cut to the T side. And then depending on how long the two endpoints are on different sides of the cut, we define the capacity of the cut accordingly. The point is that we can, first of all, prove that the capacity of an ST cut over time is an upper bound on the value of any feasible ST flow over time with time horizon T. And then when we write this problem out as a linear program, the problem of computing X that maximizes this, its dual solution, its optimal dual solution defines as ST cut over time. So by lemma 2.14, we have that this is indeed optimal. So are there any questions about max ST flows or temporally repeated flows? Okay, so now to the problem that we're interested in, the weighted maximum multi-commodity flow over time. So as before, we have capacities and transit times on every arc. We also have a time horizon T and K commodity pairs, SI-TI. We also have weights. So the weights depend on the commodity and the time of arrival, theta. So one way to think about it is we're essentially prioritizing saying kind of what time we want what commodity to arrive at its destination. So I could, there's several objective functions which one could encode using these weights. Of course, you can encode the unweighted max multi-commodity flow over time problem using them, but you can also encode things like multiple deadlines or different utility functions, for instance. You can encode those as well using these weights. So our goal is to find a feasible multi-commodity flow over time F, which maximizes this quantity here. So multi-commodity flow over time, similar to its static counterpart, consists of K flows over time from SI to TI. And when we're not going to allow storage in our setting. So because of that, we want, for any intermediate node V, we want the total excess to be 0 at any given time. We also want the capacity constraints to be satisfied. So the total rate of flow on an arc should always be less than or equal to UE. Now, the problem of computing a fractional multi-commodity flow over time is NP hard. So we definitely cannot solve this in polynomial time. Hence, it's worth asking if we can find an approximation algorithm for this problem. And in flows over time, there are two things we need to take into consideration with our solution. One is the value, and the second is the time horizon. So we define an alpha value beta time approximation as follows. We want to, the solution should have at least alpha times the value of an optimal solution, but will allow it to use a time horizon that's longer by a factor of beta. So this is by no means a exhaustive literature survey here, but we didn't see any results related to the weighted variant of the maximum multi-commodity flow over time problem. Gross and Scutella give a 1 over 1 plus epsilon value, 1 plus epsilon time approximation for the unweighted variant, which also doesn't use storage. So before we consider the general problem, let's think about a special case. Suppose the weights don't depend on the time of arrival. So our problem really is just to find an F that maximizes this quantity here. We can use the same approach as the two approximation algorithm given by Fleischer and Scutella for the quickest multi-commodity flow over time problem. So this is a problem which is, it's not the same, but it's related. And essentially what we'll do is this. So first we'll compute a static flow X that maximizes this quantity here. And then we'll compute a flow decomposition and output the corresponding temporally repeated flow F over this extended time horizon beta plus 1 times t. So note that the value of this F that we're outputting is equal to this quantity here, the weighted value, I should say. So a quick sketch as to prove that this is in fact a beta value, beta plus 1 time approximation. Let F star be an optimal flow over time with time horizon t. We'll define X bar as follows. So X bar is the average rate of flow according to F star over the entire time horizon. First of all, X bar is feasible since F star is feasible. And we also have that the value of F star I is equal to the t times the value of X bar I. Well, from X bar I, we'll define F bar to be the temporally repeated flow corresponding to X bar over the time horizon beta plus 1 times t. Okay, so what's the value, the weighted value of F bar? The weighted value of F bar is this quantity here. It's the rate at which we're sending flow times the amount of time we're sending flow along that path. And we can say that this is greater than or equal to this quantity because F star is an optimal flow over time with time horizon t. So if P is in the support of X bar, that means that F star used this path at some point. And hence, this path cannot have total transit time greater than t. Otherwise, the flow sent along this path would not reach its destination by time t. So we have that tau p is less than or equal to capital T, and hence this quantity is greater than or equal to this. From here, things simplify pretty quickly. We have that this is equal to this, and by definition of X bar, this means that it's equal to beta times the weighted value of F star, or beta times opt. Now, since the X that we compute in step 1 of our algorithm is in fact maximizing this quantity, we know that our solution will have weighted value at least WF bar. So our solution will have value at least beta times opt. And because it's a temporally repeated flow over the time horizon beta plus 1 times t, this is a beta plus 1 time approximation as well. So this, of course, if we set beta to be equal to 1, that means that we can get a temporally repeated flow of optimal value. But we have to pay a significant cost here. We've doubled the time horizon. So temporally repeated flows are actually really nice because they're efficient to compute, and it's a very elegant algorithm whenever you can use them. But does this kind of a temporally repeated flow approach work for our more general problem, which is maximizing this quantity here? And unfortunately, the answer is no, because the way temporally repeated flows worked for our special case is we lost a significant amount of the flow value. We significantly reduced the rate at which we're sending flow. But we extended the time horizon long enough that we recovered this lost value. In this case, however, the value of the flow really does depend on what time the flow arrives by. So saying that, okay, I know you wanted the flow by time 4, but now I'm going to give it to you significantly later, that's going to cause a dramatic loss in value. So we won't be able to give a reasonable approximation guarantee if we try to pursue this route. So we need to take a different approach here. What would be really nice is if we could somehow use static flows. because we have a lot of machinery for dealing with static flows. So if we could somehow represent the the flow over time as a static flow in some other network, then we could just solve the problem as a static flow problem, and that would probably be much easier for us. So from this idea comes the idea of T-expanded networks. Essentially what we'll do is we'll create T copies of node V. Each copy represents V at a particular time theta. And then we'll connect the right copies of V and W to make the edges. What I mean by that is if E equals VW is an edge in our original network, then if we start from V at time theta, we'll reach W at time theta plus tau E. So the copies we want to connect to get the edge E theta is V theta and W theta plus tau E. If we allow storage, which recall for our problem, we're not allowing storage, but in general, one can have storage. So if we allow storage, we add an infinite capacity holdover arc, V theta to V theta plus 1. So this is probably easier to see with a picture. So let's consider this graph here. Each arc has transit time 1, the first arc has capacity 3, the second arc has capacity 1. And this is a valid flow over time that I could send. So until time 1, I'm sending flow at rate 3 from S to V. And then from time 1 to time 2, I'm sending flow at rate 1 from V to T, and likewise for times 3 and 4. Note that the total amount that reaches V is greater than the amount that leaves V. So we do need to use storage. So in the T-expanded network, this flow looks like this. We had from until time 1, we're sending flow at rate 3. So here we see S0 to V1, there's a flow of 3 on this arc. Similarly, for V1 to T2, there's a flow of 1. And because we're storing 2 units of flow, there's a flow of value 2 on this holdover arc V1, V2. So I suppose what I'm trying to get at here is there's a one-to-one correspondence between a flow over time and a static flow in the T-expanded network. Meaning, in order to solve the flow over time problem, it's sufficient to solve the static flow problem in the T-expanded network. Of course, there is an issue here, and that's that the size of the network depends on T. So this would yield a pseudo-polynomial time algorithm, which is not what we want. So we need to do something a bit more clever. And Fleischer and Scutella introduced a technique which essentially constructs a smaller T-expanded network, if you will. And this technique is also used by the 1 over 1 plus epsilon value 1 plus epsilon time approximation given by Gross and Scutella. So what we do is we choose delta so that T divided by delta is polynomial in input size. And then we'll round all the transit times up to the nearest multiple of delta and divide all of them by delta. Then we'll construct the T-expanded network for this modified instance. And this network will have only T divided by delta copies of V and the corresponding edges. But we know that this is polynomial in the input size, so that means that solving any polytime algorithm on this delta condensed network runs in polynomial time. So again, let's look at an example. This is my original network, and I'm going to say that delta equals 3. So I round these 3 transit times up to 6. The transit times on these 2 arcs remain unchanged because they're a multiple of 3. Now what I'll do is I'll divide each transit time by 3 and then construct the T-expanded network. So for instance, from S to V, it takes 6 units of time, but 6 divided by 3 is 2, so I connect S0 to V2. Similarly, from S to W, it takes 3 units of time, 3 divided by 3 is 1, so from S0, I connect, there's an arc from S0 to W1, and so on and so forth. So now I can consider a static flow in this network. Say this one that's given. And the key thing to note is that 1 unit of time in this network corresponds to 3 units of time in real life. So if I take this flow and I want to look at so this is in the delta condensed network. And if I want to look at the flow in the original network, I actually get 3 flows. One starting at time 0 from S, one starting at time 1 from S, and one starting at time 2 from S. And this is why you may have noticed I multiplied the capacities by 3, even though the original network has capacity 1. And that's essentially due to this reason. 1 unit of time here is actually equal to 3 units of time in real life. So these are 3 flows in my T-expanded network. Are there any questions so far about what I've said so far? Okay, so unfortunately, this is not actually a one-to-one correspondence. It would be really nice if it were, but when we round transit times, it's possible that we take a flow which was feasible and make it infeasible. And the other direction is also true. If we have something which is feasible with respect to rounded transit times, it's possible that we end up with an infeasible flow over time in the original network. So this, of course, is bad news. So I'll show you what I mean. Let's just focus on this flow here. So I'm going to forget about the fact that I'm also sending flow at time 1 and time 2 from S. I'm only going to focus on this. So in our original network, this is what the flow over time would look like. This is our network with rounded transit times, to be specific. So by time 9, the flow sent along the bottom path reaches B, while the flow along the top path has not reached B yet. So we get that the flow from the bottom path passes through this bottleneck arc BT well before the flow along the top path does. And hence this is feasible. At every point in time, there's only flow of rate 1 on one of these arcs. Now let's look at this exact same flow in the network with our original transit times. So instead of 6, 6, 6, now it's 4, 4, and 5 here. And we see that both the flow on the top path and the bottom path reach B at the exact same time. So now we have flow of rate 2 on an arc of capacity 1. So we violated capacity constraints. So why did that happen? That happened because when we were looking at the rounded transit times, the time that it took for flow to travel along this path was longer than in the original network with original transit times. So what we could do is we can make the flow wait long enough so that we kind of simulate the rounded transit times. So what I mean is this. Instead of reaching V at time 6, our flow on this arc reaches V at time 4. So we'll make it wait for times 5 and 6. And then similarly, instead of reaching after 6 time units, the flow on this arc reaches after 5 time units, so we force it to wait for 1 more time unit. And then by doing this, we make sure that all flow, even though a flow may reach the head of an arc earlier than it did in the network with rounded transit times, it will still only continue into the next arc in its path at the same time it did in the rounded instance. Of course, in order to implement this, we need storage, which we're not allowed in our setting. But using storage allows us to do this kind of trick to resolve rounding errors in this direction. So we can get from the delta condensed network, we can get a feasible solution with respect to our original transit times. In order to give a good approximation algorithm, we need to be able to argue in the other direction. We need to be able to take the optimal flow in our original network and compare it against whatever flow we compute in the delta condensed network. But as I briefly mentioned earlier, the opposite direction also has issues. If we go from original transit times, a flow that's feasible with respect to original transit times, and go and look at it with respect to the rounded transit times, it may no longer be feasible. Unfortunately, in that case, storage doesn't help us. Here, the reason why storage helped is our problem was the anticipated times were longer than the actual times. So we can force flow to wait a bit by storing it and simulate these anticipated longer transit times. In the other direction, the anticipated times are shorter than the original times, than the actual rounded times, sorry. So by making flow wait longer, we're not going to achieve anything. What we would need to do is make flow arrive faster. But of course, you can't just disregard the transit times like that. So we need some way to resolve rounding errors when we go from the original transit times to the rounded transit times. What do we mean by resolving this? So we need to be able to prove this. And what this says is essentially, instead of thinking about the flow on this arc, the rate of flow on this arc bt, I can think about the sum of the flow that's entering B, because that flow will then enter bt. So I can think about the rate of flow on this subpath and on this subpath. And that's essentially what this quantity is referring to here. So here I have that the rate of flow entering B is the total rate of flow is 1 plus 1 equals 2. So obviously that means that I'm going to have too much flow here, and it'll be, so we'll end up violating capacity constraints. So we need to be able to argue that this is less than or equal to UE. We know this is true because F is feasible with respect to the original transit times, tau. This must be true. But how can we use this to argue about this? So the problem is that because tilde tau and tau may not be the same value, these might be two different points in time. And based on everything I've told you so far, it's not very clear how one can argue about the rate of flow at time 3, given that you know about the rate of flow at time 4. So we need some way to relate these two. There's a second issue, and that's that we don't really know how much larger this might be with respect to this point in time, since rounding errors could be arbitrarily large. So we'll deal with that issue first. We're going to make the assumption that any path has at most B edges. And if we do this, we can bound the rounding error as follows. Essentially, because we're rounding every arc's transit time up to the nearest multiple of delta, for any given arc, the rounding error for that arc is at most delta. So if a path has at most B edges, the rounding error for that path is at most B times delta. And if delta equals epsilon squared t over n, the rounding error is at most this quantity here. Okay, so that takes care of that issue. We can tell that the difference between these 2 points in time is less than or equal to this here, which is good. But we still need to be able to talk about 2 different points in time. And Fleischer and Scutella use a technique, smoothed flows, and this is also used by Gross and Scutella in their algorithm, to resolve rounding errors without storage. So this can be used both for the original transit time to rounded transit time errors, but also in the opposite direction. So the form given in their paper looks a bit different, but it's equivalent. We can write it like this because F is discrete and is piecewise continuous. So we define a moving average filter as follows. Essentially what this does is it takes our flow over time, which previously looked like this, and makes it look like this. So previously, sitting at this point in time, even though I'm within an epsilon t window of this point, I can't argue about what the value of flow would look like. But here, because I'm within the same window, I can kind of argue about how much flow is being sent at that time. So this allows us to compare different points in time, provided they're within the same epsilon g window. And this gives us the following lemma. So if we have a flow over time which is feasible with respect to original transit times, and then we smooth it using that moving average filter over time horizon 1 plus epsilon t, then every path, and if every path has at most 3 edges, scaling this smoothed flow by this factor here yields a feasible flow over time with respect to rounded transit time. And this also works in the opposite direction too. So if f is feasible with respect to rounded transit times, and we smooth and scale it by the same factor, we'll get a flow which is feasible with respect to the original transit times. So this lets us go from the delta condensed network back to our original instance and vice versa. Of course, we do have to pay, we lose some value while doing this. So this is the last piece we need for our algorithm. The first step we do is we construct the delta condensed network, as we discussed earlier. And we also add these infinite capacity arcs from S prime I to Si theta for all theta. This makes our life easier in the next step, which is we want to solve this weighted maximum multi-commodity flow problem in this delta condensed network. So note that the weights have been defined slightly differently. This is so that the value of x in this LP is equal to the value of the corresponding flow over time. And one more note, it's true that this is exponential in size, but we can use the ellipsoid method to solve it in polynomial time. So let x star be an optimal primal solution. Then we can define a flow over time as follows. And this flow over time is feasible with respect to the rounded transit times. To make it feasible with respect to the original transit times, we'll smooth it using the moving average filter, and then we'll scale it by this factor here. So we need one more assumption on our weights before we can state the result, and that's that the weights have to be somewhat forgiving. And what I mean by that is if the weights are unforgiving, so if your flow is even slightly late, then it contributes no value to your objective function. Then we'll lose quite a bit of value by smoothing the flow. Because when we smooth the flow, we're losing some value, but we recover it by extending the time horizon by epsilon t. So what we need is essentially a grace period in our weights. As long as we deliver the amount that should have been delivered by time theta within an epsilon t window of theta, we won't lose too much. We'll have at least alpha times wi theta as the weight. So we need this kind of flexibility in our weights. And if we have this, then the previous algorithm yields a solution which has value at least this factor times opt and time horizon 1 plus epsilon t. So the time horizon 1 plus epsilon t is due to smoothing the flow. The reason for these squared terms is because we need to smooth and scale the flow twice. Once when we go from the original, we take the optimal flow in the original network and translate it to something in the delta condensed network. At that point, we have to scale it by this factor to the -1, and will only be guaranteed at least alpha times opt times this factor here. And then, so now that it's in the delta condensed network, we can argue about our solution having value at least equal to this flow's value because of LP optimality. But then we need to map our solution back to something which is feasible with respect to the original transit time. In doing so, we need to once again smooth and scale the flow. And we once again lose some factor due to the nature of the weights, which is where these two squared terms are coming from. Of course, there's that special case where the weights do not depend on arrival time. And in this case, the previous algorithm yields a flow at least this factor times opt-in. the same time horizon, 1 plus epsilon t. So in terms of what we're working on now, obviously this is not the nicest approximation factor, so we're trying to improve that. We're also thinking about other related questions. So for instance, if there's a single path between every commodity pair, how does that make our life easier, in the sense that does this additional structure make it easier for us to come up with a better algorithm? And what can be said in that case? One of the possible objective functions which can be modeled, I mentioned this a bit earlier, is having multiple deadlines, different deadlines for every commodity. So for this problem, our current technique won't work because there's not a single time horizon t. Instead, we have k time horizons to worry about. So the way in which the condensed network is constructed needs to be a bit different. So this is also a question that we're thinking about. Then there's some other more general questions. So first of all, smoothing flows is one way of resolving rounding errors without storage. But are there any other ways we can resolve rounding errors? And actually, what is the role of storage for maximum multi-commodity flow over time problems? So far, at least the work that we've seen, either you assume that you have no storage or you assume you have infinite storage. But if we're given a limited amount of storage, does that help us, and can we quantify how much that would help us? So that's everything I had to talk about today. Thank you very much for your attention. Are there any questions?
First of all, let's thank Haripriya for the talk. Yeah. Questions for Haripriya?
Yeah, I have one.
Yep.
Yeah, first of all, a bunch of cool techniques. Thanks for the talk. I learned lots of things. One question I had was whether the alpha factor in your algorithm, is there some hardness result on that? Like, do you know if that's necessary?
Sorry, whether if we remove the alpha factor, if
Yeah, if there's no guarantees on the continuity of the weight functions, then maybe you like really can't get any kind of approximation.
you can get something. You can get at least what you can get something. I believe it's 1 over epsilon t. That is what the ratio will become. Essentially, what happens is that if you don't have this alpha factor, it's possible when you smooth the flow. Okay, yeah. So here, it's possible when you smooth the flow that all the weights for every other time point in this window is equal to 0. So at that point, you'll only get 1 over the window size times wi theta. So that's why when we add the alpha factor, it gives a nicer approximation bound, but we can get one. It's just that it would depend on t, so it's pretty bad.
Well, but there was a smoothing factor also involved, right? So you could have sent the flow at a time that totally missed the real value in the window, right? The value could have been at the beginning, and like as soon as you started sending flow, it's too late.
The flow will always be sent within an epsilon t window of the time when it should have reached. I'm
right.
not sure if
so I'm saying in that window, it could have been that all the value was right before you managed to send it there. Is that not possible? If you have no guarantees on f of some later time versus some previous time,
you'll end up sending some flow. You'll always have the amount you originally sent divided by epsilon t plus 1.
Okay.
That amount will always be sent at time theta.
Okay.
Now the question is, do we get from the other time points? If it's all 0, we might lose all of that. So.
Mm-hmm. Thank you.
Thank you. Any other questions?
Okay, I have a quick question. So, what happens like you also do the rounding for obtaining these delta condensed networks? The same question that Akshay was asking. Is it like what are like the limitations to this approach? Is there a way to avoid that or something? Or like how much factor is like what kind of losses are unavoidable? Something like that.
Okay, now I'm starting to understand Akshay's question a bit better. But so I don't believe that it's NP hard to, or let's put it this way. I don't think smoothing flow is the only way to do this, but we're yet to think of another way to work around this. It would make sense, although that being said, typically we do need to extend the time horizon a bit, but I'm not sure how. It is very possible there's another way to do this, and just we haven't been able to think of anything yet, or nor have we seen anything else being done.
Okay, let's thank the speaker again.